Hi guys, in this video we'll take a look at revisiting trigonometric functions, differentiating trigonometric functions using the quotient rule and chain rule, differentiating trigonometric functions with arguments of the form kx, examples, and then we'll finish with a summary.
So let's revisit the differentiation of trigonometric functions. So far, sine of x and cosine of x are the only trigonometric functions we know how to differentiate. In particular, we can differentiate the sine of x, and we get the cosine of x, and we can also differentiate the cosine of x, and we get minus the sine of x. We have previously met many other useful trigonometric functions, namely the tan of x, the cosec of x, the sec of x, and the cot of x. The last three are examples of the reciprocal trigonometric functions of their counterparts sine, cosine, and tan. We can write tan of x and the reciprocal trigonometric functions in terms of sine of x and cosine of x. So in particular, the cosec of x can be written as 1 divided by the sine of x by definition of cosec. Similarly, the sec of x can be written as 1 divided by the cosine of x. Tan of x can be written as sine of x over cosine of x. And lastly, the cot of x can be written as 1 divided by tan of x, which by the definition on the left is the cosine of x divided by the sine of x. The derivatives of the above trigonometric functions can be found from the derivatives of sine of x and cos of x using differentiation rules. In particular, the rule that dy by dx can be found by making y into a function of u, where u is a function of x, and then we have dy by du multiplied by du by dx. This is the chain rule. And then also, given a function f of x, which you can write as the quotient of functions u of x divided by v of x, in order to find f prime of x, we take the function v, multiply it by the function u prime, and then minus the function u multiplied by the function v prime. And all of this is divided by v squared. This is the quotient rule. We can use these rules in order to differentiate these trigonometric functions. So how can we differentiate trigonometric functions using the quotient rule? We can use the quotient rule to help us differentiate, for example, tan of x. The quotient rule states that if y can be written as the quotient of functions u of x divided by v of x, then if you want to find dy by dx, you do so by taking v, multiplying it by du by dx, and then minusing u multiplied by dv by dx. And then all of this is divided by v squared. So if we're looking to differentiate tan of x, then we can write tan of x as the quotient sine of x divided by the cosine of x. This gives us our u and our v. U of x is sine of x, and v of x is the cosine of x. And then, by substituting in, we have our v, which is our cosine of x, multiplied by the derivative of u, so d by dx of sine of x, and then we minus u, which is sine of x, multiplied by the derivative of v, which is cosine of x. And then this whole expression is divided by v squared, which is cos squared of x. And then we can put in the derivative expressions. The derivative of sine of x we know is cosine of x, and so when we multiply by the cosine of x over here, we get cos squared of x. And then we have minus sine of x multiplied by the derivative of cos of x. Well, the derivative of cos of x is minus sine of x. And so this minus here becomes a plus because we have two minuses. And then we get sine squared of x. And this is still divided by cosine squared of x. In order to go any further with differentiating tan of x, we are required to use the Pythagorean identity. In particular, that cosine squared of x plus sine squared of x is equal to 1 for any value of x. And therefore, when taking the derivative of tan of x, which we've reduced down to the cosine squared of x plus the sine squared of x, all divided by the cosine squared of x, we can just substitute in our result, and this becomes 1 on the numerator divided by the cosine squared of x. And then to summarise this result, the derivative of tan of x is equal to, well, by using the result that 1 divided by cosine of x is the sec of x, this expression is sec squared of x. We can also differentiate the reciprocal trigonometric functions by using the quotient rule. So if we want to find d by dx of cosec of x, or d by dx of sec of x, as well as d by dx of cot of x, we do all of these by using the quotient rule. When using the quotient rule, we use a simplified version for the ratios between 1 and a function in order to differentiate cosec of x and sec of x. We have the simplified quotient rule, which says that if we can write our y as 1 divided by some v of x, then dy by dx is equal to minus dv by dx divided by v squared. And so if we consider our y to be first equal to the cosec of x, this by definition is equal to 1 divided by the sine of x, and therefore we're going to let our v be sine of x. So in order to find our dy by dx, where y is equal to the cosec of x, we're going to use our above simplified version of the quotient rule, and we get the minus of dv by dx, which is the derivative of v, which is cosine of x. And then we divide this by v squared, so we divide by the sine squared of x. We can split this up into two expressions. Namely, we can have the minus outside, and then the cosine of x divided by the sine of x, and then we can multiply this by 1 divided by the sine of x. And therefore, we get minus the cot of x multiplied by the cosec of x by their respective definitions. And so, to summarise this result, the derivative d by dx of cosec of x is equal to minus cot of x multiplied by cosec of x. Similarly, if we instead now let y be equal to the sec of x, then this is equal to 1 divided by the cosine of x, and so it is sensible to choose our v to be this time the cosine of x, the expression on the denominator. So then in this case, in order to find our dy by dx, we again use the simplified quotient rule, and so we need minus the dv by dx divided by v squared. Well, v is cosine of x, and so dv by dx gives us another minus. And so we have the minus out front, and then we have the minus sine of x from dv by dx. And this is divided by the cosine squared of x, that is the v squared. So then the minuses cancel out, and we can separate this expression into two expressions, just like we did before, and we get the sine of x divided by the cosine of x, and then this is multiplied by 1 divided by the cosine of x. Again, the minuses from before have cancelled out. And then this is nice because this gives us the tan of x multiplied by the sec of x. And so, to summarise this result, we have the derivative d by dx of sec of x is equal to the tan of x multiplied by the sec of x. When using the quotient rule for cot of x, we need to recall again the Pythagorean identity. In particular, again, that the cosine squared of x plus the sine squared of x is equal to 1. So, when differentiating the cot of x, we can do so by differentiating the cosine of x divided by the sine of x, because that is an expression for cot of x. And then we can apply our quotient rule. A nice way to think about it is in terms of the numerator and the denominator. And so we get the denominator function, which is sine of x, multiplied by the derivative of the numerator function, which is the derivative of cosine of x, and then we minus other way around now, the cosine of x multiplied by the derivative of sine of x. And all of this is divided by the sine squared of x. By replacing the derivatives, we have cosine of x goes to minus sine of x, and so we get a minus sine squared of x. And then we have minus cosine of x multiplied by another cosine of x from the derivative of sine of x, and so we get a minus cosine squared of x. And all of this is still divided by the sine squared of x. And then notice that this numerator is just minus sine squared of x plus cosine squared of x, which is 1. And so we get minus 1 divided by the sine squared of x. And so finally, we can summarize this result, and we have that the derivative of the cot of x is equal to minus the cosec squared of x. This is the 1 divided by the sine squared of x. We can summarize all of our results below. Firstly, we showed that the derivative of tan of x was equal to sec squared of x. Then we showed that the derivative of the cosec of x was equal to minus cot of x multiplied by cosec of x. And then we showed that the derivative of sec of x was equal to tan of x multiplied by sec of x. And then finally, we just showed that the derivative of cot of x is equal to minus cosec squared of x. These are the 4 results that we just showed. So how can we differentiate trigonometric functions instead using the chain rule? We can use the chain rule to help us differentiate the reciprocal trigonometric functions. So for example, we can differentiate cosec of x, sec of x, and cot of x using the chain rule. Firstly, we can differentiate cosec of x using the chain rule. Recall that the chain rule says that dy by dx is equal to dy by du multiplied by du by dx. So if we want to differentiate the cosec of x, we can write this as d by dx of sine of x to the power of minus 1. And then we can use our sine of x as our u, and so we get this is equal to d sine of x to the power of minus 1, and then by d of sine x. Again, we are choosing our u to be sine x, and then we multiply by d sine x by dx. For the first one, we get a minus sine of x to the power of minus 2. Again, if you're not comfortable with this, you can use the chain rule more carefully by actually substituting u equals sine of x. And then we multiply by d sine of x by dx, which is cosine of x. And then finally, we can write this as minus the cot of x multiplied by the cosec of x, just by separating up one of the sine of x to the power of minus 1 with the cosine of x to give us the cot of x, and the remaining sine of x to the power of minus 1 gives us the cosec of x. We may also differentiate sec of x using the chain rule. So, if we want to differentiate the sec of x, we can write sec of x as cos of x to the power of minus 1, and then using the chain rule, this gives us d of cos of x to the power of minus 1 by d cos of x. Again, we're using our u as cos of x, and then we multiply by d cos of x by dx. And so for the first one, we get a minus cos of x to the power of minus 2, and then we get another minus from the d cos of x sine x, because we get a minus sine of x. We can instead write this as the tan of x multiplied by the sec of x, firstly because the minuses cancel out, and then we can bring one of these cos of x power of minus 1s with the sine of x to give us our tan of x, and the last one gives us our sec of x. We can also differentiate cot of x using the chain rule. So now we can differentiate the cot of x, and we can write cot of x as tan of x to the power of minus 1. And as we've just done using the chain rule, we get d tan of x to the power of minus 1 by d tan of x. Here we're using our u equals tan of x, and then we multiply by d tan of x by dx. This gives us minus tan of x to the power of minus 2 multiplied by sec squared of x, because the derivative of tan of x is sec squared of x. And finally, we can write this as minus cosec squared of x. This is because the sec squared of x cancels with the cos squared of x from the tan x to the power of minus 2, and we just end up with our cosec squared of x. We can summarise these results of differentiating trigonometric functions below. Firstly, if we differentiate the tan of x, then we get the sec squared of x. Similarly, if we differentiate the cosec of x, then we get minus the cot of x multiplied by cosec of x. If we differentiate the sec of x, then we get tan of x multiplied by sec of x. And lastly, if we differentiate cot of x, then we get minus cosec squared of x. These are our 4 results for the derivatives of these trigonometric functions. So how can we differentiate trigonometric functions with arguments of the form kx? We have seen how we can differentiate sine of kx and cosine of kx from first principles. In particular, we reach the results that d by dx of the sine of kx is equal to k multiplied by the cosine of kx. And similarly, we found that d by dx of the cosine of kx is equal to minus the k of sine of kx. Alternatively, we can use the chain rule again to show these results. Recall that the chain rule states that dy by dx can be split up into the product of dy by du multiplied by du by dx. So if we'd like to differentiate the sine of kx, then we get d of the sine of kx by d of kx multiplied by the d of kx by dx. This may seem a bit strange, but it is entirely simple to understand. We take our sine of kx, and then we have this input here, kx, which is common to both. And if we differentiate sine of kx with respect to kx, we're just going to get cos of kx. If that still feels unfamiliar, you can write u equals kx, and then you get y equals sine of u, and then that becomes cos of u, which is cos of kx. But this is a slight shortcut. And similarly, the derivative of kx with respect to x is just k. And so as we saw, we get k multiplied by the cosine of kx. And similarly, if you'd like to differentiate the cosine of kx, then we can do so by taking d of cosine of kx by dkx, and then multiplying by dkx by dx. Differentiating cos of kx with respect to kx gives us minus the sine of kx. And then differentiating kx with respect to x gives us k. And so, as expected, we get minus k multiplied by the sine of kx. These results can be extended for the remaining main trigonometric functions by the similar applications of the chain rule. As a result, when we differentiate the tan of kx, then we get k multiplied by the sec squared of kx. Similarly, if we differentiate the cosec of kx, we get minus k multiplied by the cot of kx multiplied by the cosec of kx. Similarly, when we differentiate the sec of kx, we get k multiplied by the tan of kx multiplied by the sec of kx. And finally, when we differentiate the cot of kx, we get minus cosec squared of kx. These are the 4 rules corresponding to kx as the argument of these trigonometric functions, and when k is equal to 1, we get precisely the results we had before. Let's take a look at some examples. Our first example asks us to differentiate y equals cot of 5x plus 2 using the chain rule. Our first step is to recall the chain rule. We have that the chain rule is dy by dx is equal to dy by du multiplied by du by dx. Our second step is to convert the function into a composite function by introducing a new variable in terms of x. Our expression is y is equal to the cot of 5x plus 2. If we let our u be equal to 5x plus 2, then we reduce y to being y is equal to the cot of u. Our third step is to record the derivative of the cot of x. In general, if we differentiate the cot of x, then we get minus the cosec squared of x. Our fourth step is to calculate dy by du and du by dx. Firstly, dy by du. Well, if we have y is equal to cot of u, then differentiating both sides with respect to u and using the above rule gives us minus cosec squared of u. And then similarly calculating du by dx, we have by our definition of u that u is equal to 5x plus 2, and so very simply we have 5. Our fifth step is to use the chain rule to find dy by dx in terms of x. So again, when calculating dy by dx, we're going to be using the chain rule, which gives us the product of dy by du and du by dx. And therefore, by multiplying these two quantities together, we get a minus 5 cosec squared of u. And then finally, by re-substituting our u back in, we get minus 5 multiplied by the cosec squared of 5x plus 2. And this is our final answer for the derivative. Our second example asks us to find the derivative of y equals 2 lots of sec of 3x plus 1 all squared using the chain rule twice. Our first step is to recall the chain rule. We have that the chain rule is that dy by dx is equal to dy by du multiplied by du by dx. Our second step is to convert the expression 2 sec of 3x plus 1 all squared into a composite function by introducing a new variable in terms of x. We have our y as being equal to 2 lots of the sec of 3x, and then plus 1, and then all squared. And so if we take our u to be this inside expression, which is 2 sec of 3x, and then plus 1, then we get that y is simply equal to u squared. Our second step is to recall the derivative of sec of kx. We have that d by dx of sec of kx is equal to k multiplied by the tan of kx multiplied by the sec of kx. Our fourth step is to write down the derivative of sec of 3x. So therefore, by substituting in k equals 3, we have sec of 3x being differentiated, and we just put in k equals 3 everywhere, so we get 3 multiplied by the tan of 3x multiplied by the sec of 3x. This is effectively our second application of the chain rule. In order to get this 3x as our argument for the sec and then to differentiate it, we've had to use the chain rule. Our fifth step is to calculate dy by du and du by dx. We have our dy by du, and by looking at our y in terms of u squared, differentiating this gives us 2u. Similarly, our du by dx, by looking at the expression for u in terms of x, u is equal to 2 sec of 3x plus 1. And so all we need to do is multiply this expression here, the rule for the derivative of 3x, by 2 to both sides, because the plus 1 differentiates to 0. And so we get 6 lots of the tan of 3x multiplied by the sec of 3x. Our sixth step is to use the chain rule to find dy by dx in terms of x. Well, we know by now that we take these two expressions and multiply them together. And so we're going to get for our dy by dx, just by multiplying these two expressions together, the constant outside is 12, and then we have a u, and then a tan of 3x multiplied by a sec of 3x. We're not done quite just yet, because we need to resubstitute our u in terms of x, and u is equal to 2 sec of 3x plus 1. And so, by putting our u to the end, we get 12 lots of the tan of 3x multiplied by the sec of 3x, and this is all multiplied by 2 lots of the sec of 3x plus 1. We could expand this out, but this is in quite a nice factorised form. and this is our final answer. Our third example says that given that f of x is cosec squared of x, we're asked to solve the equation f prime of x equals 2f of x for minus pi strictly less than x strictly less than pi. Our first step is to recall the derivative of cosec of x. We have that when we differentiate the cosec of x, we get minus cot of x multiplied by cosec of x. Our second step is to find f prime of x using the chain rule. The chain rule states that dy by dx is equal to dy by du multiplied by du by dx. And again here, because we have our f of x being cosec squared of x, we're going to be using our u as being equal to cosec of x. And then we have our f of x being u squared. So again we have our u being cosec of x, and then as a result we have our y, or rather our f of x, as being equal to u squared. And so when we differentiate and get f prime of x, this is going to be equal to, by differentiating our f of x with respect to u, we get 2u, which is going to be 2 lots of the cosec of x, and then we multiply by du by dx. Well, this gives us a minus cot of x cosec of x. And so we end up with a minus 2 lots of cosec squared of x multiplied by cot of x. Our third step is to rewrite the equation f prime of x equals 2f of x in terms of x. F prime of x is equal to minus 2 lots of cosec squared of x multiplied by cot of x. And 2f of x is 2 lots of cosec squared of x. Our fourth step is to simplify the equation. We have a 2 lots of cosec squared on the left and right hand side. Now cosec of x is equal to 1 over sine of x, and so can never be 0. And therefore it's acceptable to divide by 2 cosec squared of x, and therefore we keep a minus cot of x on the left hand side, and then we get a 1 on the right hand side, and then by flipping we get a tan of x is equal to minus 1. This is 2 flips. What we have done is to multiply both sides by tan of x, and so we get a minus 1 and we get a tan of x. Our fifth step is to solve for x in the required range. We were given the range minus pi to pi strictly. By using a calculator, we see that the tan of 3 pi over 4 is equal to minus 1. This is within the range we need. And similarly, we're able to add and subtract pi in either direction, and we get the same result. Adding pi gives us a value outside the range, but subtracting pi doesn't. So similarly, the tan of minus pi over 4 will also be equal to minus 1. And therefore, the solutions of the equation are x is equal to minus pi over 4 or 3 pi over 4 in the range we have.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together, let's make A-level maths a walk in the park.